going to do that real quick again for Easton's benefit. But again, we know that when we have so we know that when we have compression of the spring to this point, remember that the potential energy that we have is 1/2 kx squared. We figured out how we determined that. And since that's A at that point, we can say that that's 1/2 Ka squared. Okay, and then as the mass comes back to the equilibrium point, all of that potential energy is being converted into kinetic energy. And since it's conserved, we can simply set the equation for kinetic energy equal to the equation for potential energy. The 1/2s cancel out, and I want the velocity. So I'm going to divide both sides by m, and then I'm going to take the square root, and I know that a comes out of that square root, so velocity is going to equal a times the square root of k over m. Okay, and you said that was answer B. Okay, so, and how good are you guys at just doing this kind of manipulation in your head real quickly? So you're not quite as fast as me, but
yeah.
Okay, but you need to get to that point. Okay, a lot of these problems they become a lot easier if you can do a lot of this manipulation in your head, and you know it just takes a little bit of practice. You're just thinking here, well, I need to isolate this, so how am I going to isolate that? I need to divide by m, then I need to take the square root, and I know that a is going to come out. And so anyway, that just takes a little bit of practice, and you'll get better and better at that all the time. Okay, so a force, so that's again a conservation of energy approach to solving problems. And it's a lot different than our force analysis approach. We could find the velocity by analyzing the forces and using motion equations just as easily as, well, not just as easily. It would be a lot harder to do that because we've got a changing force. But we could do that using force equations and net force equations, free body diagrams, and things like that. But it's a lot easier in some circumstances to use a conservation of energy approach. Force F at an angle theta above the horizontal is used to pull a heavy suitcase of weight mg at distance d along a level floor at a constant velocity. The coefficient of friction between the floor and the suitcase is mu. The work done by the frictional force is, this is a tough question because it leads you into a couple of different directions. So a good thing to do for this would be to draw a little diagram. To kind of, I wish I could draw on the thing there. Okay, so I'm going to be pulling the suitcase at an angle theta above the horizontal, and that's my force, okay? And I'm going to be pulling it for a distance d. And I want to know what the work done by the frictional force is. Now, one thought would be that since I'm pulling it at a constant velocity, that the work that I'm doing in this direction is going to be the opposite of the frictional force. So I could say that the frictional force, or the work done by friction, is the opposite of the work done by the applied force. So if I wanted to think about this one way, I could think of the work of friction equals the opposite of the work done by the applied force. And that would mean I'd need to figure out how much work was done by the applied force. Okay, and I know that that's going to equal the opposite of force D cosine of theta. And remember, we don't have to worry about figuring out what that force is in the x direction. Our formula does it for us, right? So don't take the cosine of that to find the force in the x direction and then do that a second time, okay? So we don't want to do that. But we could then say that that equals negative FD times the cosine of theta. Wow, that just solved it, right? Why did I think that was such a difficult problem?
So we didn't even need the coefficient of friction.
Well, but there's another way that you can go about doing this. Okay, and we want to make sure that we do it in the most efficient way.
Yeah.
We also know that, I'm just wondering why I thought this was so difficult. We thought about the coefficient of friction. So if we went that way, what's the formula for the force of friction?
Mu, not mg.
Mu Fm force normal.
Okay. So, but in this case, the normal force is actually it's not going to just be mg, is it, right? Normally it's mg if
it's just a straight.
Yeah.
So we have an angle. So it would be mg.
The vertical component of force.
So it would be mg
Minus the vertical component of force. Yeah.
Okay, times mu, yeah. So, come on, Jay. So that's what that would be?
Yeah.
So if we tried to figure it out that way, we could too, okay? So we could say that the force of friction is going to be mg minus f sine of theta times mu. But there's not that answer up there, is there? So, and it's hard to know just by reading the problem which way is going to be the best way to go. But I think, this obviously proved to be by far the easiest way to do that.
Yeah.
I'm not sure how to tell you how I would have decided which way to go without having done the problem before.
Well, would they give you stuff that you don't actually need to try to?
Oh yeah. Yeah, all the time.
Okay.
Yeah, so you actually didn't need that. Okay, a 2 kilogram ball is attached to a 0.8 meter string and whirled in a horizontal circle at a constant speed of 6 meters per second. The work done on the ball during each revolution. Okay, here's where your memory of what work is done on an object in circular motion comes in. What's the direction of the force in circular motion?
And
Towards the center of the circle. What's the direction of the velocity?
Out.
Straight line.
Straight line, right? Okay, so they're perpendicular to each other, and that means what as far as work done? Because cosine of 90 degrees is 0 degrees. How much work is done on the object?
None.
0, okay? So if you know your stuff, that's like a 2-second question.
Yeah.
Okay? If you remember that work done on any kind of a circular motion thing by the force, the centripetal force, it's going to be 0.
That's cool.
The pendulum bob of mass m on a chord length L is pulled sideways until the chord makes angle theta, with the vertical shown in the figure to the right. The change in potential energy of the bob during the displacement is, okay, so while I'm getting a new screen here, any thoughts on how to deal with this?
Is this like circular motion? No?
We want to know how much potential energy the plumb has, or the bob has now. Okay, and what's the only thing that matters in terms of deciding that?
Displacement?
In what direction? Is it displacement along the arc of the path, or is it displacement in the vertical direction?
It's vertical.
Okay, so the only thing that's going to determine how much work I did is the vertical displacement here, right? How far did I move it up? Doesn't matter how far I moved it along this path. The only thing that matters is at this point it has a little bit more potential energy than it did at this point. What happened to it in between doesn't matter. Here it's got a potential energy, here it's got a potential energy. I want to know what the difference in potential energy is there. Okay? So I need to figure out, though, just exactly what that is. I know that work equals force times distance times the cosine of theta. Okay? And in this case, we're saying that all of our force is going to be in the same direction as the motion. We're going to say that our force is actually taking it upward, and the direction of the motion is also upward, because that's the thing that we're trying to figure out here. So cosine of theta isn't going to come into play here because the, well, it's going to come into play, but not in the way you think it does, because cosine of that angle is going to be 0. Or cosine of that angle is a cosine of 0, which is 1. So it's just going to be force times distance. Okay, so I want to know the force is going to be what? That's required to move it up that distance.
Work times distance or work divided by distance?
Okay, you're thinking too much. So if I raise an object from here to here, how much force do I need to use?
Direct opposite of mg.
Okay, so it's going to be mg, right? So mg. Okay, now I need to figure out what the distance between these two actually is. Okay? And I know what the length of this chord is. Right here, this is L. This whole thing down here is L. Right? From here down to here is L. But I need to know what this distance is right here. Okay? So it's going to be L minus something. Okay? It's going to be L minus something. And it's going to be L minus whatever that is. And if this is theta, and if this is the hypotenuse, and this is the adjacent side, hopefully it would make sense that this length right here is going to be L times the cosine of theta. Okay, this side, this adjacent side of this triangle right here is going to be L minus, the whole thing is L times the cosine of theta, and that's what we want. So L times the cosine of theta, once again, this is L cosine of theta, and the whole thing is L, so it's going to be L, the whole length, minus L cosine of theta to determine what this little length is right here. Does that make sense? Okay, so L minus L times the cosine of theta, because that is also L, right? And so that distance is going to be mg times L minus L times the cosine of theta. And oftentimes, they'll take the L out of there, and then it just becomes mg L times 1 minus cosine of theta, which is A. Okay, so in these kinds of problems, you're almost always going to have to find one of the lengths of the sides of this kind of a triangle, and you're probably going to have to find that and subtract that length from the actual length. And unless someone shows you how to do this kind of a problem the first time, it's not something that you would easily figure out if you saw it for the first time on a test. Okay. We'll do one more of these, and then we'll talk about conservation of energy. Softball player catches a ball of mass m, which is moving towards her with horizontal speed v. While bringing the ball to rest, her hand is moved back a distance d. Assuming constant deceleration, the horizontal force exerted on the ball by the hand is what? And you can imagine, right, when you're a catcher and you catch a fastball, you bring your hand back a little bit when the ball hits but over that space, that couple of inches that your hand moves back, the ball is also stopping at the same time. Okay, so as you're doing that, you're doing work on the ball, and the ball is doing work on your glove. Okay, so assuming a constant deceleration, the horizontal force exerted on the ball by the hand is, okay, what relationship is going to help us be able to figure out this? What theorem is going to help us be able to figure this out? What did we call the theorem that explains the relationship between work and kinetic energy? Maybe the work energy theorem?
Yeah, that would make sense.
Oh, I thought it was something like fancy guy's last name.
Nope, the work energy theorem.
Oh, that's very nice.
You remember that from a couple times ago, right?
Well, now I do.
Okay. So work energy reminds us that 1/2 mv squared equals force times distance. Okay? This is a work energy approach. We have two different ways we can do things with these problems. We either have a conservation of energy approach, where we end up setting the potential energy equal to the kinetic energy. 1/2 mv squared equals 1/2 kx squared, or 1/2 mv squared equals mgh, depending on which type of potential energy we're talking about. Or we have a work energy approach, where we know that work and energy are also the same thing, so we can set those two formulas equal to each other to help us find out something here. And we want to know what the force is, so all we have to do is divide 1/2 mv squared by d, and that would be mv squared over 2d. Is that one of our answers?
Mm-hmm.
Does that make sense?
Yes.
Okay. almost everything we can accomplish in all of these problems is going to take some form of either conservation of energy or work energy. Okay? So let's talk about conservation of energy for a few minutes back in our notes. The thing that thrills me so much about physics is that there's such an internal consistency in all of it. I mean, it all fits together and it never seems to fail. It's never incorrect. It just, it all works out if you know the right rules. And it just kind of, every time I see how consistent it is, it just kind of amazes me. But conservative and non-conservative forces. Can I get one of you guys to shut that door for me, please? I'm sorry. No. Sorry about that. Okay, so consider the following two scenarios. Carrying a box of 50 newtons up a flight of 20 meters in height, and carrying a box of 50 newtons along a 500-meter rising and falling trail, which at the end is only 20 meters higher than the starting elevation. Okay, so what we're thinking about here is that what is the direction of the force on the box? It's upward, right? Now, you could argue, well, you're using a little bit of friction on your hands to move the box, horizontally, but we conveniently just sort of ignore that fact. And when we're talking about work and energy, we're only going to be talking about the main aspect of this. And in this case, I'm moving a box 20 meters above where it was before. And in this case, I'm moving a box 20 meters where it was before. All that matters in either of these scenarios is the beginning and the ending circumstance, because all we're doing is changing the amount of potential energy here. Okay? Now, you could argue we're also adding kinetic energy to the box, but that's only while the box is in motion, right? We come to a stop again and all that kinetic energy is gone. Any kind of work that we might have done in the horizontal direction is gone. But when I carry this box up 20 meters or I carry this box up 20 meters, even if I've gone up high mountains and come back down to a point that's 20 meters above there, the only amount of work that I've done is the amount of work that shows me what the difference between the potential energies is. Okay, so in either circumstance, because the force applied is only in the vertical direction, only the vertical displacement counts in determining work. And again, yes, you could argue that there's some horizontal force too, but we're conveniently ignoring that. Work equals force times the cosine of theta, 50 newtons. Okay, and while I'm carrying this box, I'm only applying a force that's equal to the weight of the box. How do I know that?
Because it's not accelerating.
Yes, it's not accelerating. Thank you. I love that answer. I've told it to you enough times, right? But I'm glad that it's there and it sticks. But anyway, 50 newtons in the upward direction times 20 meters in the upward direction. And again, force is upward. Direction of motion is upward. There's no angle of distance between those. So cosine of 0 degrees is 1, and 1 times 50 times 20 is 1,000 joules. So we did 1,000 joules of work in accomplishing this. Now, let's be really precise about what we understand here. We actually may have done a lot more work personally, but we added 1,000 joules of potential energy to the box. Okay, and that's what this is really saying here. We added 1,000 joules of potential energy to the box. You can say, well, it certainly seems like I did a lot more work in this circumstance than I did in the other circumstance. And you may feel that way, but as far as the box is concerned, hey, I got 1,000 joules of potential energy that I didn't have before at that lower position. Okay, so forces for which work done depends only on initial and final position are called conservative forces. Conservative forces, those for which the path taken to accomplish the work does not matter, include the force due to gravity, spring force, electrical force, and magnetic force. Okay? Now, recognize that when we do work against gravity, or we do work against a spring, or we do work against an electrical force, or we do work against a magnetic force, all we're doing is changing the amount of potential energy. The object that we move with relation to one of these forces either has more or less potential energy than they used to. For example, if I have a positive charge here and I have a positive charge here, and I move this positive charge to this point, I did work on that charge to move it closer because there's a repellent force there, right? There's a force pushing against that. I did work against that electrical field, and I now changed its potential energy. It has the ability to do more work than it did before. Okay? Likewise, if I pushed the negative end of a magnet closer to the negative end of a magnet, there's a repellent force there, right? And this magnet now has a greater ability to do work than I did before, but it's still all just potential energy. I've stored potential energy in this magnet, or in this charge, or in that spring. Now, obviously, if I do it the other way, to store potential energy in this magnet here, this negative magnet, I'm going to have to pull it away, right? Okay, I'm going to have to pull it away, and that will store potential energy in that. In all of these scenarios, the amount of potential energy that I'm going to store is related to the distance from it, right? However far I moved it. And again, that makes sense. Work is force times distance. Now consider the other two following scenarios. Pushing a box 50 newtons to a position 20 meters away in a straight line. Okay, so over there, I pushed it from there to there. Or pushing a box to a position 20 meters away along a winding path. So I pushed the box to this position, but I took a circuitous path, but it's still a flat surface that I'm pushing it on. In each scenario, the direction of the force is always in the direction of the motion. No matter what direction I'm pushing the box here, that's also always going to be the direction of motion, right? So again, my cosine of theta is going to be a value of 1. So whatever I do, I'll multiply that times 1. But in the first scenario, I only pushed it 20 meters along this surface here, and so I only did 1,000 joules of work. But since I pushed it along a 500-meter path here, and I'm not going up or down, I'm just following a straight path, well, a curved flat path, I did 2,500 joules of work. Okay? And in this case, the work that I did depend on the path, right? Okay, I'm pushing it along a friction surface here, and so when there's a non-conservative force, the path does matter. Okay, if there is no non-conservative forces, the path doesn't matter. It's a conservative thing. If the force that I'm using is non-conservative, that it takes energy away from what I'm doing, then it's a path that the direction does matter. Non-conservative forces include friction, any kind of mechanical force, any push or a pull, tension in a cord, motor or rocket propulsion, air resistance. All of these are non-conservative forces. I'm adding something or taking something away from the system by my accomplishing that force. So what about the work done by conservative and non-conservative forces? So we previously developed the idea of work energy equivalence. This is a concept that the amount of work accomplished on an object gives rise to the equivalent amount of kinetic energy. And we also did that for potential energy too, right? When we were storing energy in a spring, for example, we said the work that we did equaled the amount of potential energy that we got. Now we extend the idea to include work performed in circumstances where there might be both conservative and non-conservative forces involved. Okay? This is another one of those things where I'm going to walk us through a mathematical analysis of this that you don't need to know, okay? Just like the analysis that we use for centripetal motion, you don't need to be able to do that geometric proof that showed that the centripetal acceleration is v squared over r, okay? Even though that's entirely not intuitive unless you use that geometric approach. This is another one of those kinds of derivations that you don't have to know, but if you're familiar with it, it really helps your understanding. So let's write an equation for network involving both conservative and non-conservative forces. And hopefully it makes sense that the network that we do equals the sum of the conservative and the non-conservative work. Okay, that's going to make sense. And in all likelihood, the non-conservative work is going to oppose the conservative work. And so one of these things will likely have a negative value. And you hope that in whatever scenario it is, that you're going to at least get a little bit of actual work out of it. You don't want the non-conservative work to completely cancel out the conservative work. Okay, so we know that the network also equals the change in kinetic energy. Okay, so work equals work conservative plus non-conservative equals the change in kinetic energy, because that's the what theorem?
Work energy.
The work energy theorem. Yay. It's the Marshall theorem. Now, this would allow us to write an equation to describe the work performed by non-conservative forces in terms of conservative forces. So if I want to know something about this, hopefully that means that I can isolate this and compare it to whatever else is left. So I'm going to say just what you might think then. The non-conservative work equals the change in kinetic energy minus the conservative work. However, we have also just stated that the work involving conservative forces only involves change in potential energy. Therefore, I can substitute that. Recall that the work done by gravity is the opposite of the change in potential energy. And let me remind you of that. If I lift a box up here, let's say it's 10 newtons, and I lift it 10 meters, and I know that the amount of potential energy I added to that box was mgh, and mg is 10 and h is 10, so that's 100 joules. I added 100 joules of potential energy. At the same time, since we're saying that we raised this at a constant velocity, the amount of work that gravity did in the opposite direction is negative 100 joules. Okay? So we can say that the work done by gravity is the opposite of the work done by some force that creates a change in potential energy. The work done by gravity is the opposite of the change in potential energy. I changed from 0 to 100 here, so the change in potential energy, delta PE, is 100 joules. Gravity did the opposite of that. And I've said consider the raising of an object from a lower potential to a higher potential. And so this is when I get confused, and I get confused about this a lot because this is really a difficult concept. When I get confused, I always go back to this scenario because it's the one that teaches me this relationship, that the change in potential energy is the opposite of the work done by gravity. Okay? So the work is done against gravity. The direction of this motion is the opposite the direction of the force of gravity. So in this circumstance, an increase in potential energy represents the opposite of the work done by the conservative force. Okay? The increase in potential energy represents the opposite of the work done. This would be similar for any conservative force. An increase in potential energy would represent work done against the conservative force. So I can say that the work done by the conservative force is the opposite of the change in potential energy. Okay? Hopefully that makes sense. The work done by the conservative force here, gravity was the conservative force. The work done by that was negative 100 joules. But that is the opposite of the change in potential energy, which is 100 joules. Hopefully you agree that the opposite of 100 newtons is the opposite of 100 newtons. So we can now substitute this in for the previous equation. We had negative WC over there, right? So we had delta KE minus the work of the conservative force. But since I can say that that's the opposite of the change of potential energy, that means this is added to it. So the work performed by non-conservative forces equals the total change in kinetic energy and potential energy. The work done by non-conservative forces equals the total change in potential and kinetic energy.
And then work done by conservative is negative potential change of potential?
Yes. Yes. Okay. Now, again, you don't have to internalize this discussion, right? You don't have to understand it in order to figure out what we're going to do next. But if you do, especially if you go on into physics and of electricity and magnetism in college, that understanding will help you immensely. Okay? The way we define things is really screwy once we get into electricity and magnetism. And if you understand this idea, it will help immensely. Now, it will often be that in order to simplify the analysis of work energy problems, we'll ignore possible contributions done by non-conservative forces. How often have we said, there's no friction, there's no friction, there's no friction, right? We ignore possible contributions of work performed by non-conservative forces, especially friction and air resistance. After we get the basics down, we can add those back into the picture. So, in circumstances where we can ignore conservative and non-conservative forces, total mechanical energy is conserved. Okay? If I say that, and check this out, we already said that the work of the non-conservative forces equals the change of potential energy plus the change of kinetic energy, right? If I'm saying I can ignore that, that means there is no non-conservative forces. The work done by non-conservative forces is 0 joules. Therefore, by definition, it's not just something we created or cooked up. By definition, the change in kinetic energy equals the change in potential energy. Okay, well, it equals the opposite of the change. So it's absolutely 100% true that if my box drops from a height, that all of that potential energy will now become kinetic energy. If I ignore the fact that my non-conservative air resistance is probably slowing it down a little bit. Okay, if I ignore that, then we've just proven that kinetic energy equals potential energy. Now, they don't make you do that on an AP test, prove that, but if you have that in your brain, that's very, very powerful. Okay? My recommendation, though, is just, hey, I know that there's a way to prove that the potential energy and kinetic energy is conserved when I don't have non-conservative forces. That's all we really need to understand here. So that's the same thing as final kinetic energy minus initial kinetic energy plus final potential energy plus or minus initial kinetic energy is the same thing. Or we can rearrange that to say KE2 plus PE2 minus KE1 plus PE1, right? If I say this plus PE2, right? KE2 plus PE2 minus KE1 plus PE1, that's going to equal 0. Or I can say KE2 plus PE2 equals KE1 plus PE1. The sum of the kinetic and the potential energy when I start up here equals the sum of the kinetic and potential energy when I started. Okay? Now, we're going to call the sum of kinetic and potential energy the total mechanical energy, or E. Why might we call this mechanical energy? We're going to call the sum of potential and kinetic energy at any point the total mechanical energy.
I want to say because it's moving, and so thereby it's changing it, but I don't know.
Okay, so that's really close to, I mean, there's not a real good answer to this question other than that, because this is what we see in the mechanical world. This whole discussion is called mechanics. All of these forces and motions that we're talking about is called mechanics. This whole branch of physics is called mechanics. So it might make sense that we call the total energy of the mechanics world mechanical energy. Okay? It's the energy of the things that I can see. Okay? And that's how I like to think about it, versus the energy of the things that I can't see, which involves the changes in energy that occur at an atomic level. Okay? Which is vastly more difficult than this. Okay, so anyway, the total mechanical energy is Ke plus Pe. Therefore, in situations where we can ignore non-conservative forces, total mechanical energy is conserved in before and after situations. Because of the conservation of mechanical energy for any situation where we can use this principle to analyze energy changes, any loss of kinetic energy is accompanied by an equal loss, or any loss or gain of kinetic energy is accompanied by an equal loss or gain of potential energy. We can expand the above definition of total mechanical energy to include formulas for Ke and Pe to help us in problem solving. But be sure to pay attention to the fact that solving problems using conservation of mechanical energy gives exactly the same result as using kinematic formulas to solve problems. I can solve them using either way. Okay, so I know that the total mechanical energy is going to be 1/2 mg squared plus mgy or mgh, however you want to say it. And I know that kinetic plus potential energy in the after situation equals kinetic plus potential energy in the before situation. So, if the initial height of a falling rock is 3 meters, calculate the rock's velocity when it has fallen to 1 meter above the ground using a conservation of energy and appropriate kinematic formula. So I'm going to do this two ways here. Okay, so our procedure for conservation of energy processes, if we have a discrete before and after situation, is I'm just going to write out 1/2 mv2 squared plus mgy squared 2 equals 1/2 mv1 squared plus mgy1. Okay, and I'm going to try to eliminate some of these. The initial height of a falling rock is 3 meters. Calculate the rock's velocity when it has fallen to 1 meter above the ground. In the initial circumstance, do I have any kinetic energy? I don't, do I? So I can cancel that out. Okay? And I want to know what the velocity, the final velocity is. So I'm going to first say 1/2 mv. Oh, I can also cancel out all my m's, can't I?
Oh yeah, you can.
That's always nice. So I'm going to say 1/2 v squared equals g times y1 minus y2. Right? Because I'm going to move this over here, and then I can factor out the g. Okay? Then I can multiply both sides of the equation by 2 and take the square root. So I'm going to say that v final velocity equals the square root of 2 times g times y1 minus y2. And if we simplify things here and use 10 for g, and we multiply 2 times 10, which is 20, and y1 minus y2 is another 2, so that's 40. Okay, so the square root of 40, is that right?
Yes.
Okay, and that would be 2 times the square root of 10.
Yeah.
Meters per second. Okay, let's see if we get the same result using our kinematic formulas. Okay, so have I been given time here?
No.
So what formula do I have to use?
V squared, no. Forget it. V0 squared plus 1/2 2.
You're mixing your formulas.
Yeah, it's been a while.
Okay, my initial velocity is 0, right? Okay, so V equals, wow, the square root of 2a, which is g, right, times x1 minus x2, so x minus x0, which in this case is y1 minus y2. How cool is that? It's exactly the same formula. That just blows my mind. This is, like I said, this is what thrills me about physics, the fact that this is so internally consistent that, I mean, it has to be, I can't imagine what Newton must have felt like when he was perceiving all of this in his brain. This must have been so thrilling to him because nobody had really synthesized things like this before he did. Okay, consider the height of a roller coaster hill to be 40 meters. Calculate its speed at the bottom of the hill. At what height will it have half the speed? Okay, now the other thing that we can do is we can just write out what we already know is going to be in the formula. We don't have to write out kinetic energy plus potential energy equals kinetic energy plus potential energy. At the top of a roller coaster, it hasn't told us this. It hasn't told us that it's moving with any velocity. So we're going to assume that it's not moving at all at the top of the hill, right? It's going to start with a velocity of 0. So my initial kinetic energy is going to be what?
0.
0. Okay, so on the right-hand side of the equation, and you can do this backwards, right? You can say my initial position equals my final position if that is easier for you. I like to say my final is equal to my initial, but so I know that for my initial, I'm only going to have mgy1, and then at the bottom of the hill, I'm just going to have my kinetic energy, right? I'm not going to have any more potential energy, so I'm going to say 1/2 mv2 squared equals mgy1. Okay, and I want to know what the speed at the bottom of the hill is going to be, so it's going to be the square root of 2gy1 equals, and again, we're going to use 10 here, so 20 times 40, so the square root of 800. And let's make sure our units are working out here. What's the units of the acceleration due to gravity?
Meters per second squared.
And then for y?
Meters.
Okay, so if I take the square root of meters squared per second squared, I get meters per second, which is what I want. Okay, so what's the square root of 800?
28.28. So on the top one, we answered it in 2 square roots of 10. Can we answer all of the questions like that, or do we have to?
They'll tell you. Okay, so they'll tell you if they will allow you to use 10 instead of 9.8. Okay, sometimes they won't. Okay, at what height will it have half this speed? And you better not say half this height. Because velocity is increasing by a square, right? It's not increasing linearly. It's increasing by a square. So, am I going to be able to turn this around and then just find y maybe? So I can say 1/2 mv squared 2 equals mg y1. Is that the height that I want though? Okay, so this will be...
Yeah, that's... Because that's the height of the top of the hill.
Yes, so that's okay. So that will work, won't it? So I want y1 now, don't I?
Yeah.
So I can still cross out. Something about that doesn't seem quite right, but let's see what happens.
If it has half that speed, would it not still have potential energy at that point?
Yes, it would. But that is the... Oh, I see what you're saying. So, so we're going to have to add in a second factor here, huh?
Yeah.
Yeah.
Okay, so how would we do that at that height? At what height will it have half that speed? Okay, so it still doesn't have an initial that, right? So we're going to say 1/2 mv2 squared plus mg y2 equals mg y1.
And then we want to find y2.
Yeah.
Yeah.
And then we want to find y2. Okay? So let's get rid of the m's. And then we can say gy2 equals gy1 minus 1/2 v2 squared. And then we can say y2 equals gy1 minus 1/2 v2 squared over g. And it's always better, even though you can cancel that one out, you can't cancel that one out, so it's always better to just go ahead and put it under the denominator. So let's say 10 times, what was y1, 40 meters?
Yeah.
Minus 1/2. And at that velocity, or at that point, it would be 14.15 meters per second.
Yeah. Wouldn't it be 1.4 because we rounded up?
Oh, did we?
Yeah, because it was 0.28 instead of 0.3.
Okay.
Yeah.
They wouldn't matter. It wouldn't matter on the test. And that's squared, right? Divided by 10. Okay, I don't have my calculator here, so.
$29.98.
29.98. That doesn't seem right, does it? That seems too close to 28.3. Okay. Is that what you got?
I got 39.29.
So like a half a second after it
Yeah,
left.
that doesn't make sense either.
Okay. So we did something wrong, didn't we?
Yeah.
Okay. Why don't you see if you can figure out between now and next class how this problem should actually work. And we'll come back and see if we can't do it justice.